All right, so here we go. We got the derivative with respect to x of the integral of that function from log base 2 to cotangent of x. So there are two ways to do this. You can either try to find the antiderivative of that and evaluate it and then take the derivative of it. And that's not going to be the way I would go because finding the antiderivative of that, does anyone know what it is off the top of your head? Yeah, me neither. Or there's another way to do it, right? Using what part of the FTOC? Part 2, which says what? It basically says that the derivative and the integral are what? Related how? They're inverses of each other, so they'll undo each other's work. So if you're taking the derivative of the integral, your final answer will be some version of the original integrand, right? Which is that radical function right there. But we're not going from a plain old constant to a plain old x, so it's not just going to be the plain old integrand. Rather, we can use that general rule, which says to do what first? Plug in the top, right? So for everywhere there's a t, we're going to plug in the upper interval of integration, which is cotangent of x. So we plug in cotangent of x. And then what? Right, times the derivative of what you plugged in. So that's the derivative of cotangent, which again is a great way to review the derivative rules. The derivative of cotangent is negative cosecant squared, okay? And the parentheses there, I would again encourage you, dot negative, right? Dot negative, but dot parentheses negative, wow. Minus, right? Minus, not plus, but minus, and then we plug in the bottom, do the same thing. We're going to have log base 2 of x squared, oops, I forgot the O, there we go. Log base 2 of x squared plus log base 2 of x. And then we multiply by the derivative of log base 2 of x, which of course everyone remembers is? Good. Yeah, yesterday we saw the one where it was exponential. That was not base e. We multiply by the natural log of the base. Here for logs, we divide by the natural log of the base. And then from there, we're done. We're not going to simplify, okay? Simply because we can. And if we can, we don't have to. All right? Okay, so then to the notes. Let's see how far we can get today. I'm hoping we can get close to concluding this section. We are on 4.3. All right, so we talked about the MVT for integrals yesterday, and the MVT for integrals basically said if a function is continuous on a closed interval, then there's a C value where? In France? In the closed interval, which means it could be an endpoint, where the y value at that C value gives us a what? It gives us a height, yeah, which we call the average value, such that the area of the rectangle over the same width is the area under the function, yeah, or the net accumulation, right? And so we're really after the average value. That f of c gives us a way then, by a density method, to figure out what the average value is of whatever we're measuring on the y-axis when it happens through a continuum. When there's infinitely many things, we can't just find the arithmetic mean. We have to do it this way. All right, so we did that with the temperature. We found the average temperature. Every once in a while, you might have to find the actual value. So just to review that, if it asks you to actually find the value guaranteed by the theorem, you do the average value first. You find it. And, of course, how do you find average value without looking? Yeah, integral over width, right? Integral over width. That gives you the average value. Now, you got to be careful because if the multiple choice question said to find the value guaranteed by the theorem, that's an x value, and you find the average value to be 2, guess what probably answer choice A will be? 2, right? Which is the y value, not the x value. So if you need the x value, you set the original function equal to your average value, and then you solve that equation. And once you get your x value, then you must make sure that it is actually where, Schroeder? In France? Not Zimbabwe. Unless your closed interval includes Zimbabwe. So if you're going from Zimbabwe to France, you got to make sure that your value of x is on that closed interval, right? So if we had come up with like a 3, of course, we wouldn't include it. But in this case, the thing that, again, is worth pointing out is that if it does show up as an endpoint, for the MVT for integrals, we can't include it. It's only the MVT itself, which is for derivatives, that excludes the endpoints. The IVT, the EVT, and the MVT for integrals all allow the endpoints to be the value. Okay, so here we go, example 14. The word average now is going to show up quite a bit, and we need to make sure that when it says average, we know exactly what to do. Because there's average rate of change, and now there's average value. So just to kind of go over it again, if you're looking for the average rate of change of a function, how do you do that? Average rate of change is? It's the difference quotient. Good. You don't use calculus at all, right? It's just the change in y over the change in x. The average value, of course, is integral over width, which is the integral over the change in x. Yeah. All right, so it says to show that the average rate of change of a car's position over time from t1 to t2 is the same as the average value of its velocity over the same interval. Oh, that's a lot of words. The average, let's start with the first part. Show that the average rate of change of a car's position over time from t1 to t2. So let's go ahead and give the position function a name. What do you want to call the position function for the car? Give it a name. S, P, L, K, J, M. How about S? Okay. We usually use S for position. I'm going to use script letter S. So we'll let S of t be the position of the car in terms of t. All right. So if I'm trying to find the average rate of change of position on the interval from t1 to t2, then the average rate of change of position, what's another way to say average rate of change of position? What do we call the rate of change of position? Wow, look at his position change. He is fast. Speed, right? Or in general, velocity, right? So the average rate of change of position is velocity. So anytime we're talking about rate of change, there's two types, right? Average and instantaneous. The instantaneous requires calculus. The average does not. What do you call the rate of change of velocity again? Acceleration, right. So the average rate of change of position is the average velocity, and of course, it's the difference quotient. It's the final position, S of t sub 2, minus S of t sub 1. And remember, that by itself, if we just look at that, gives us another meaningful quantity. That's the what? Just the change in position. Final minus initial is? Your net change in position is called? Displacement. Good. Okay, this is kind of a review of particle motion, which it's coming up again. There's a whole other section on particle motion using the integral. But that's a displacement. So if you do the rate of change of position, or the change in position over the change in the corresponding time, again, that is the difference quotient, and that does give you the average velocity, or the average rate of change of position. So remember that the quotient will come out to give you the same numeric answer if you did S of t sub 1 minus S of t sub 2 over t sub 1 minus t sub 2. But you don't want to get in the habit of doing that. You always want to get in the habit of doing final minus initial, because then the numerator by itself then is meaningful. All right, so that's as far as we can get without any numbers or any function. So there's the average rate of change of position. Now it says to show that that's the same as the average value of the velocity function. Okay, so let's go ahead and find the velocity function. How do we find the velocity function? That is, as a function of a single variable t from the position equation. S prime. So S prime of t, let's give it a name. How about V for velocity? That's reasonable. Okay, so now that I have the velocity function, like if I had the graph, it would be measured on the y-axis. Once I have the velocity function, how do I find its average value? The integral. Okay, so now the average velocity, since it's the function that I have, is the average value, not the average rate of change, because the average rate of change of velocity would be the average acceleration. So here we go. It's the integral now from t sub 1 to t sub 2 of vt dt all over t sub 2 minus t sub 1. All right, so to evaluate the numerator, let's see. I would need to know the antiderivative of big V. What's the little v maybe. What's the antiderivative of velocity? Position, right? So it would be S of t. We don't need the plus c. And then I would evaluate it from t sub 1 to t sub 2. And of course, that's still all over t sub 2 minus t sub 1. And now using the fundamental theorem of calculus, part 1, to evaluate that, I plug in the top minus I plug in the bottom all over the change in the corresponding time. Is that the same thing we got over there? It's exactly the same. Yeah. And you would expect them to be the same. Otherwise, it really wouldn't be worth studying. So whenever you're asked to find average velocity, I said to be careful when it asks you to find average of anything, but especially if you're asked to find average velocity, because that could be found one of two different ways. If you have the position equation and they ask you to find the average velocity over an interval, and you have the position equation to start with, that's the average rate of change. That's the difference quotient. If they start you off where you have the velocity function in hand and you're asked to find the average velocity, it is now the integral over the width. So you need to really make sure that you know how to find it depending on what you're given, right? One's average rate of change, one's average y value. Okay, cool. Now, I guess if you have the position function and they ask you for the average velocity, if you don't want to do the average rate of change, you could do what? You could take the derivative and get the velocity function and then do the average value. We just proved that they're exactly the same. That's just a little bit extra work. Quite a few bits of extra work. All right, so questions on example 14. Moving on. How many more do we have? Oh, we got a few. Okay. Example 15. The table below gives values for a continuous function. Is our function continuous? Yep, says so. Does that mean it's also differentiable? Is every continuous function differentiable? No. Is every differentiable function continuous? Yeah, that's the way it works. Okay, so using the values given, find the arithmetic mean of f of x, and then use a trapezoidal approximation with 6 subintervals to estimate the average value. Okay? All right, so the function's continuous, but this is what I was saying the other day, that if you have like temperatures changing, you can't really go out and measure them continuously. So you go out at regular intervals and you take readings. So here's some y values maybe that were collected at these different values of x. The arithmetic mean is just another way to say the average, the average that you're used to finding. So how many values do I have there? 1, 2, 3, 4, 5, 6, 7. Are you impressed? So here we go. If I'm trying to find the arithmetic mean, that's also known as the average, it's going to be the sum of those numbers divided by 7. So help me out with the sum here. 42 plus 38. I guess I need to indicate my method. 42 plus 38 plus, there's going to be a lot of them, 31 plus 29. If someone has a calculator right now, we won't call that cheating if you'd like to do it. 35 plus 48 plus 60. Of course, on a free response, you wouldn't even have to compute that. You do want to make sure that that division bar goes all the way across. Anyone got it? If those were your grades, oh, by the way, I didn't take it for granted. I'm adding up the what? The x values or the y values? What? I'm adding up the x values? No, I'm adding up the y values. Yeah, I want to find the average y value. What did you get? 40.428. Thank you, Schroeder. Schroeder, everyone. Yeah. Okay, so what that does, remember, is it just takes into account the y values at that moment. This is really a continuous function, and we don't have any idea of what happens in between there. But if you were to plot the points randomly, and it was a continuous function, you might connect the dots, realistically with some type of curve. So adding up those discrete y values is not a bad way to get an average, but it does kind of miss some of the material or what's happening in between those points. And so if you do a trapezoidal approximation now, what you're going to be doing is doing it by the density method, which does take into account possibly what's happening in between there. It kind of infers it. And that's what we're going to do next. We're going to find the average value by using the trapezoidal method, and it should come out to be somewhere in the neighborhood of 40. So here's another way to find the average value. The average is going to be, let's see, I have to approximate the integral using the trapezoidal method. So I'm going to go ahead and write it first. It's going to be the integral from 20 to 50, the integral from 20 to 50 of f of x divided by 50 minus 20 dx. Thank you, dx. Okay, so now I put an equal sign there, but I should backtrack because now I need to put a squiggle because I'm approximating the numerator with the trapezoidal method. So let's see what the delta x is first. Okay, we're going to use as many subintervals as the data allows. Notice your subinterval width conveniently is what? It's a constant 5. So I can factor out the 1/2, of course, for sure, and the 5 I can also factor out. And when you can factor out your delta x, then you can expedite the process because you're going to use all the y values, and remember the interior ones get used twice. But since they're associated with the same width on either side, you can just double them. So you're going to have 42 plus twice 38 plus twice 31. And Schroeder, if you could jump on this too, I would be maybe not eternally indebted, but at least for the rest of the day. Oh, okay. Nice. Y'all just decided that between the two of you to divvy it up between the two Austins. I think so. It must be. Right. And we divide that by, now we can show 30. Stanford. Right, Stanford. Are you sure someone else is on it? Berquist, you got it? Oh, yeah. Okay. So you could put a 12th in the denominator. The sum of the brackets divided by 12. Oh my gosh. Memory cleared. Yeah. Uh-oh. You got it. Well, not yet. Well, not yet. Let it go. All right, let it go. By the way, while they're doing that, the answer at this point is almost trivial because on a free response, you're demonstrating understanding, you're demonstrating knowledge, and that right there says it all. Right. I got any monkey with a calculator can type it in. Yeah. What? Uh-oh. I got 38. Oh, wait, divided by 30. Come on now. 38.6. There we go. 0.666? We better call it 667. Thank you. Better call it 667, the neighbor of the beast. Yeah, 38 is a lot more reasonable. Hey, we had some issues this morning. We were trying to figure out how fast the Earth was traveling around the sun in its orbit, and we used the wrong radius, and we came up with 2 miles per hour. Yeah, and what was good is that the students were like, I don't think that's right. I mean, they knew it was not reasonable. Y'all remember what it was from pre-cal? About 66,000 miles per hour. We're traveling around the sun, and then while we're doing that, we're spinning at over 1,000 miles per hour. So yeah, pretty cool. But anyway, 38.667 is pretty close to 40, so I'm guessing that's a good way, or that was correct. Now it says, if possible, determine which one is more accurate. How are we going to know which one's more accurate? We'd have to compare it to what? The real average. Do we know that? No. But in general, if you have a continuous function, which method is better practice than the other? The trapezoidal, yeah, or any kind of area method. And remember, the trapezoidal is a little bit better in general than the left and right endpoint because it's not as extreme with the over and under approximations. So that works for a continuous function. For like discrete values, like your grades, the trapezoidal method doesn't really make sense. So yeah, the trapezoidal method. Or Simpson's method, which we don't really know. There's another way to do it. Or using a Taylor polynomial possibly or something like that. But maybe ideally you put these points into your calculator, right? And you know whether or not this data came from some type of exponential or polynomial or sinusoidal function, and you can actually fit a curve to it. And once you can fit an actual curve to it, then you can go ahead and do the integral on the calculator divided by the width. So yeah. Here we go. It says sometimes we might have to solve an integral equation. Sometimes we might have to solve an integral equation. That's good to know. That's good to know. Being able to simplify definite integrals with variables in the interval of integration is important here. A couple of above. Okay, I don't usually like to read that stuff. Yeah. Okay, example 16. Let's just see what it is. Example 16. Find the number or numbers. Ooh, look at that. Foreshadowing. Right? Foreshadowing. There might be more than one, or two, or three. B. We're calling the numbers B. There might be more than one B, but we're going to find them such that the average value of this function on the interval from 0 to B is equal to 3. Find the number B such that the average value of that quadratic on the interval from 0 to B is equal to 3. So, okay, first notice that the variable is the the upper bound of this process. So, in general, you could just say, okay, I got a parabola, it opens down, and I'm going to be integrating from, looks like maybe 0 to B. And what I want to do is find the value of B so that when I integrate on that interval, whatever it is, the average value ends up being 3. Okay, and so you can kind of see that maybe we have to slide our B value left and right in order for the average to become 3. So that's what we're doing, right? And with notability, we can do this. This is one of the advantages to notability. Hard to do this on paper, right? Unless you have your own TV show, right? Because it would be magic. That was the stretch. Right. Right. That'd be a guy that comes behind you and has another TV show that shows you how you're doing it. Right. Right. And he would be masked. Have you seen those shows on Fox, like the Masked Magician showing how you do silly tricks? All right. So here we go. Let's go ahead and set it up. Average value. Average value. Is that average rate of change or average value? Hey, it's a silly question, but it's one you should ask yourself. Average value. Yeah, it's almost embarrassing to answer it, right? Yeah, it's average value. So how do we find average value? Over, yeah, width. And what was the first part? Yeah, integral over width, integral over width, integral over width. So here we go. We're going to take the integral, and because I'm doing it by hand, I'm not going to put f of x in there. I'm going to go ahead and write the function. Make sure you have parentheses around all three terms, and I'm integrating from 0 to b. So I'm going from 0 to this unknown b, and then I'm going to divide that by the width from 0 to b, which is b minus 0. And that has to equal what? 3. So there you go. You have an integral equation. And notice now b has shown up twice in the problem. He is no longer just in there once. He's in there twice. He is the upper limit of integration, and he's also in the denominator. So now we have to solve for b. This is a conditional equation. And what we do with conditional equations is we solve them. So there's a couple ways to proceed. You can either pull the b minus 0 out front and call it 1 over b times the integral, or you can actually multiply both sides by b. What would you want to do? I would multiply both sides by b, because it's a conditional equation. We can do that. So you're going to have a 3b over here. And now, on the left side, I can go ahead and start finding the antiderivative of that polynomial, which is easy, right? The power rule. So we got 2x plus 3x squared minus x cubed. Do we need a plus c? No, it's a definite integral. And we evaluate it from 0 to b. And then we can kind of remodel over here. We can kind of lasso that with scissors and bring it over. So far, so good, right? Now what? Plug in the top minus plug in the bottom. So we got 2b plus 3b squared minus b cubed. And then all of that minus, and in general, it's good to put minus parentheses, right? But what happens when you plug in the 0 for x? You get 0, right? 0 plus 0 minus 0, which is 0. So if you didn't show that, that would be okay. But just because you have a 0 in your bottom interval of integration or anywhere in the upper interval of integration doesn't mean you're going to get 0. Because if you had like an e to the x in there, e to the 0 would be 1. So don't not think, I should say. So I end up with 2b plus 3b squared minus b cubed equals 3b. Sweet. And now I get to solve that. How do I solve something like that? By factoring. But before we factor, we got to get everything on one side instead of equal to 0. It doesn't make sense to factor unless you have it equal to 0. So I'm going to bring everything over to the left side so that my leading term b cubed is positive. So I got a 1b cubed, and then I got a minus 3b squared, and then I'm going to have a negative 2b plus the 3b that's already there becomes a positive b. And there you go. Now, luckily, there's no constant, right? Whew. If there were a constant, we would be kind of trying like to do trial and error or something like that so we can find at least one root to synthetically divide out. But the fact that there's no constant means that I can do what? Pull out a common factor. And we're left with b squared minus 3b plus 1. And that equals 0. And now what? They're quizzing on this today in Algebra 2. Huh. F it! I thought we already did. Partially. It's partially F'd, right? We're going to see if we can F it some more. Are there factors of 1 that add up to -3? Factors of 1 that add up to -3? No. Thank goodness we have that tattoo, right, of the quadratic formula. No, let's go to the quadratic formula. It's going to be the opposite of b. b is -3, so it's +3, plus or minus the square root of b squared. Be careful. b squared, if b is negative, is going to be positive. So -3 squared is 9, minus 4 times a is 1, times c, which is 1, all over twice a, which is twice 1, which is still 2. All right, so now we get b equals 3 plus or minus, let's see, 9 minus 4, that's the square root of 5 over 2. So there's your conjugate pair. If you want to write them in the standard form, you get 3 halves plus or minus the square root of 5 halves, for what it's worth. And you get b equals 0. So there appear to be 3 values of b that work. And going back to the question, it said to find the number or numbers. So yeah, I was maybe anticipating there were more than one. Now, which one of those makes sense? All 3 of them? Is every quadratic? What, you mean y-axis symmetry? Yeah, if you look at this, we're looking on the interval from 0 to b, and one of the numbers showed up as 0. So if we go from 0 to 0, do we technically have an interval at all? No. And so 0 actually doesn't make sense in the context of this problem, and so it's not going to be a viable solution. Okay, so that's one of them. What about the other 2? So let's see, we have 3 halves. I'm going to split them up. Plus the square root of 5 over 2, and then 3 halves minus the square root of 5 over 2. This is positive, right? Yeah, we just need to make sure, because that one's subtracting. If one of those ends up being a negative number, does a negative number make sense here? No, because we're going from 0 to something. So you just got to make sure one of them is, or they're not negative. Square root of 5 is about what? About 2 point something. So 2 point something divided by 2 is like 1 point something. 3 halves is 1.5. Is 1.5 minus 1 point something greater than 0? In this case, it is, right? Because all you have to do is compare the numerators, right? You go 3 minus, it's almost better to put it back like that, yeah? Square root of 5 is 2 point something. 3 is bigger than 2 point something, so it's going to be positive. Yeah, so all you need to do is determine that it's positive. You don't need the actual value. So both of those values do work. Both of those values work.
Why did we exclude 0 again from the interval?
Well, b is the upper bound of the interval. And because we're talking about an interval, if you go from 0 to 0, you don't even have an interval. So it doesn't make sense in this problem. So this makes a nice multiple choice question, because you get 3 answers, and maybe 0 is an answer choice in one of them. Maybe one of those answers that you end up with is a negative number, and if you try to include it, it doesn't make sense either. So solving integral equations, that's what we set up here. It's a conditional equation with an integral in it, and to solve it, we basically evaluate the antiderivative using the fundamental theorem. We'll be doing a lot of that again in chapter 6. Chapter 6, all about integration. All right, so there was your first taste of an integral equation. Any questions on that? Average value, we set it up. Average value. How do you find average value? Something over with. What's the first one? Integral. Good. Average rate of change? Difference quotient. Good. All right, example 17. Solve the following conditional equations for the indicated variable. All right, we got the integral from -5 to x of t cubed minus 7t with respect to t equals 0, and we're going to solve it for x. I'll let you try it on your own. We just solved the conditional equation, right? You know how to do this. You got this. You don't need me. You don't need me. I'm going to go ahead and pass out your thingamajigger, my bobbers, while you're doing that. And this makes for great online video right here. Read your grade? Yeah. Austin B. I won't give the last names because it's going on the YouTube. Austin B.
My address is.
Yes, Social Security number. Cat D. Mr. Erickson. I won't give your first name, Thomas.
Changing it up.
Yep. There you go. Internet famous. Yeah, all 3 people that watch in the next 10 years. No, if you look at the total views, it's total views right now. It's about 144,000. Just an FYI. That's total views. Total views. Yep. Most of y'all go to the shared folder now, right? When you look at videos, I hope. Either one. I'm not putting the links on the YouTube. There are on YouTube, but the links don't go straight there. The shared folder is the way to go now. You can watch them on your iPad, supposedly. It takes a while to load them, I heard. Austin number, we're going to call you Austin number 1. So I'm going to go from left to right from my vantage point. Yeah. I thought you were the one calculating, and I saw you not typing, and I was like, Schroeder was throwing me off. It was Austin number 3. Would you rather be Austin A or Austin 1? You more of a numbers guy or a letters guy? Up to me. Okay, well, let's go with numbers. I've already named you. I don't want to change the engraving. Vanessa, congratulations. I heard. There you go. There you go, Lauren. Brandon. Colton.
South.
Yes, the South Pole. Where's that? Huh. Okay, so here we are. Y'all are working it. I see that. You got the antiderivative. I'm going to try and catch up with y'all. If you have a conditional equation, make sure that you keep both sides as you work your way down. 1/4 t cubed. Let's see the 4th. I don't know. I was reading over Schroeder's shoulder. Ooh. Gross. Who wrote this problem? Right. Huh? Yucky, yucky, gross, gross. I didn't even know if I'm doing it right. We got the same thing. That's a good sign. That bodes well for me. All right, so if you want to look up here, we're just jumping in reflexively, right? We see we have an integral equation, and it's an easy antiderivative, right? Assuming you know how to do it, right? Have a 4 there. You evaluate it from -5 to x. So plug in the top in parentheses, it becomes a function of x minus plug in the bottom very carefully, because you got some negatives here. Yeah, the numbers come out to be kind of gross, and I think I got them right. Marissa, 350. Oh, dang it. Thank you. Where? This 250 should be a 350. Oh, indeed it should. Yeah. And that should be a 275. Thank you. Yeah, there we go. 275. Thank you, Austin, for your compliment. Thank you. All right, so anyway, if they come out to be ugly, I cleared out the 4s instead of working with fractions, just because I didn't want to do that. And then you get down here, and you got something like that. Now, that main factor, it's a quadratic, but it's a quadratic in terms of x squared. So you got x to the 4th and x squared. So maybe that factors into x squared plus or minus something, x squared plus or minus something. It doesn't have to be an x squared and an x. As long as the larger one is twice the middle one, it can factor into the middle one. The question is, what are some factors of 275, and are there any that add up to -14? Man, we might need some help with that one, huh? Unless we just want to go out on the adventure and seek. So let's kind of, before we complete that, let's kind of take inventory actually and make sense of what we're actually doing, huh? That makes sense. Because you can get so caught up in the algebraic process that maybe there's a more elegant way to do it, or maybe something will kind of give you a hint. We're trying to find the net accumulation from -5 to x of t cubed minus 7t. Now, look at t cubed minus 7t. I'm not sure what the graph actually looks like, but you could get a little hint. If you factored out a t and you get t squared minus 7, it looks like it passes through the x-axis at 0 and then plus or minus the square root of 7, something like that. And because the leading coefficient is positive, I know it's going to exit the top, and it's a cubic, so it's going to come in the bottom. Now, this function actually, if you notice, has some type of symmetry, because both exponents are odd. When you plug in a negative t, you're going to get out the opposite of what you do if you get a positive t. So it has what type of symmetry? Origin symmetry. And we're integrating from -5. So let's go ahead and mark that. Let's use pink here. So let's say this is -5. We're trying to find the x. That is the upper interval of integration, so that when I start integrating from left to right, I get a net accumulation of 0. You should know one of the solutions immediately without doing anything. 5 or -5? -5. Yeah, -5 for sure works, right? Because the integral from -5 to -5 of any function is going to be 0. Because remember, you haven't accumulated anything if you haven't gone anywhere. So there's one of the solutions already. Now, because of the symmetry, we saw this with the little sine and cosine activity. Whatever I pick up there, maybe there's another one over here that I pick up that'll cancel. And if I pick something up here, I'll lose it over there. So what's the value of x over there that makes that perfectly cancel out? 5. So I have two solutions, x equals 5. Now, that might be enough. There might be another place, right? Because as you start picking up this region here, if this region here is smaller than that, then there might be a place where I pick up some negative, and as I switch to the other side of the x-axis, maybe the portion above is actually bigger, and maybe I zero back out somewhere in here. So it could be that I have another 0 right here. And then after that, I'll pick up some positive, which maybe then it zeroes out again right here. And then, of course, it could cancel. So it looks like there could be 2 more places where it could happen, or 0, which means we can have maybe 4 solutions, right? Well, look what this degree is. It's a 4. Huh, surprise. Now, we could use the fact that we know two of the solutions, either A, to help us factor this, or synthetically divide it out, whichever you want to do. Because what we know then is that if negative 5 and 5 are roots, this is going to factor into x minus 5 and x plus 5 times something else. And so you could do one of two ways. You could say that that's x squared minus 25, and then you can do long division, do the fourth degree polynomial divided by the quadratic, and come up with your quotient, which would be the other factor. Or you can do what? Maybe use x squared minus 25 as a way to help you factor it, right? We already said it factors maybe into x squared plus or minus something.
Teachers, please find this interruption.
How many quarters are in 275?
December 2015 EOC.
11?
Please stop by the back office to take us through scores.
Now it has to be a plus.
If you're participating in the cookie dough fundraiser, please make sure you turn in your forms today to Coach Starr.
Does that work?
And could you please turn to
Negative 25 times 11 is negative 275. Yep. Negative 25x squared plus 11x squared is negative 14x squared. It works. So you keep it equal to 0. So you can either do it that way, or you can use synthetic division here. You'd have to write out your coefficients. 1, 0, negative 14, 0, negative 275. Synthetically divide out of 5. Synthetically divide out of negative 5. And you'll be left with the coefficients 1, 0, 11. So however you want to do it, here's the factorization. Now the only other two possibilities are going to be the roots of x squared plus 11. Are there any real solutions to that? No. So the two that we found were the only two. So x equals plus or minus 5. But it could have been that there were two other solutions. So geometrically, it's always nice to understand what it is you're doing. So as it turns out, this region that was below was, the area of that region was greater than the area of the region above, because it never zeroed back out. But had the graph been, gone up a little bit higher here, like maybe like that, I don't know if it's possible to do that, but now we'd pick up some negative region, and then of course the positive region would maybe equal the negative region right about there. And so we'd get back to a net accumulation of 0. But it didn't turn out that way. The numbers didn't lie. All right, so there you go. Let's see if that'll help us over here. We're trying to solve for k now. The integral from negative 3 to k of x squared minus 4. Maybe we look before we leap now. We come down here to negative 4, and we sketch what the graph is doing. It looks like that. It looks like that. And the x-intercepts are at negative 2 and positive 2. So notice we're integrating from negative 3. So what do you know for sure if we're going for a net accumulation of 0? One of the solutions is already before you start. Negative 3, right? You don't go anywhere, you don't accumulate anything. So that's one of the solutions. Well, let's see how many more there might be. As I integrate from left to right, I pick up a region that's going to be what? Positive or negative? Well, from left to right, it starts off positive, right? Now, as I go underneath, notice there's a huge region underneath. So there will likely be a space right about here maybe where I get back to 0, where the areas are of equal size but opposite in magnitude. So maybe I zero out there. So there would be another one. Now I come this way, and now I'm picking up a whole mess of negative region. And as I cross, that's the only time I cross, there's definitely going to be a place, right, somewhere over here where I zero out again. And then after that, what happens? Now it's positive forevermore. So it looks like I should have how many solutions? 3 total, all right? And I already know one of them. So let's go ahead and proceed. Can I use symmetry here to help me? Is k equals 3 also going to be another one? No, not necessarily. It might turn out that way, like if it were like a sine graph or something like that, or a cosine graph with symmetry. But these lobes are not necessarily symmetrical. That only works with an odd function. So let's go ahead and do it the old-fashioned way. We'll actually integrate it by hand. 1/3 x cubed minus 4x from negative 3 to k. Keep it equal to 0. 1/3 k cubed minus 4k, parentheses, minus plug in your negative 3 and you get negative 9 plus 12. I did that quickly. Negative 27/3 is negative 9 plus 12. Looks right? So we get a 1/3 k cubed minus 4k, and that gives us a minus 3. Now you have a fractional coefficient there, which you're free to work with, but if you want, what could you do? Multiply everything through by 3. And you end up with k cubed minus 12k minus 9, and of course 0 times 3 is still 0. Now, of course, that's a cubic polynomial. As we saw up above, there's up to 3 solutions. Like they're doing in Algebra 2 right now with synthetic division, it's nice to get down to a quadratic because then we can use the quadratic formula, as we already saw, if we can't factor it. So in order to do that, we would need to know at least one solution. Do we know one? Yeah. And this one is not going to factor as nicely as the other one because it's x cubed, and that's not x to the 1.5 power. So it's not going to factor nicely into like 2 binomials. So in this one, I guess we can use what to help us get down to the quadratic? Either long division, because we know that x equals -3 is a root. That means that k plus 3 is a factor. We'll do it like that. And you can either do long division or synthetic division. And I prefer the synthetic. So Colton South is going to do long division, and I'm going to do synthetic, and we're going to compare answers. All right, so you got 1x cubed. Don't forget your placeholder, 0x squared. Then your -12 and your -9. And we put our root, which is -3, right there. All right, so then we bring down the 1, prime in the pump, and then we multiply, slide it up, and add. And we should get a 0 here. If we don't get a 0, that means something's wrong. There we go. So we know that that factor is really now to k plus 3 times, these are the coefficients down here of your quotient, which is 1 degree smaller, k squared minus 3k minus 3. Okay, so now we're kind of back to where we were earlier. We try to F it some more, right? But to factor this quadratic trinomial, we need factors of -3 that add up to -3. Do we know what they are? No, but again, thank goodness we have that tattoo that we got. It was good money spent, right? Because we can always reference it, and we can use the quadratic formula. The opposite of -3 is 3 plus or minus the square root of 9 minus, it ends up being plus 12 all over 2, if you kind of speed things up because you know the bell's coming. 9 plus 12 is 21. Any simplifying there? Square root of 21? 7, 3, both prime? No. So you can call it 3 halves plus or minus the square root of 21 halves, and of course you got -3. Now, do we need to make sure that both of those are positive in this case? Is this one of those issues? No, because you could integrate from right to left. That's not a big deal. So if one of them ends up being smaller than -3, which I don't think it is, because then we're just picking up negative area forevermore. So there they are. There's 3 solutions. And we anticipated in this case that there would be 3 solutions, because I think it was pretty obvious that the region below the x-axis was much greater than that little part above that we started with. Okay, we'll pick up tomorrow with example 18. Apparently it's a very important example, so you don't want to miss it. If you do, make sure you check out the videos. So we will finish tomorrow. So it looks like the worksheet for this section is going to be due on Monday, I told y'all. Yeah, so that's fine if you want the weekend to do it. Never not Friday. Okay.